Greetings to all. Today I am going to explain about the simulation of Dpsk transmitter and receiver using Simulink software. The aim of the experiment is to generate and demodulate differential phase shift keying signal using Simulink. The software used is Simulink software. Coming to the theory of Dpsk, it involves two basic operations at transmitter: differential encoding of the input binary wave and phase shift keying, hence the name Dpsk. To send symbol 0, we phase advance the current signal waveform by 1800, and to send symbol 1, we leave the phase of the current signal unchanged. In the differential encoding, at the transmitter, input starts with an arbitrary first bit serving as reference, and thereafter the sequence is generated using dk-1, previous value of the differentially encoded digit. Bit error rate, that is BER, in digital transmission, the number of bit errors is the number of received bits of data stream over communication channel that have been altered due to noise interference, distortion, or bit synchronization errors. The bit error rate or bit error ratio BER is the number of bit errors divided by the total number of transfer bits during the study time interval. This BER is a unitless performance measure often expressed as percentage. In a communication system, the receiver side BER may be affected by transmission channel noise, interference, distortion, bit synchronization problems, attenuation, wireless multipath fading, etc. The BER may be analyzed using stochastic computer simulations. If a simple transmission channel model and a data source model is assumed, the BER may also be calculated using binary symmetric channel, the additive white Gaussian noise, which is AWGN channel without fading. Now, let us see the procedure to draw the Dpsk transmitter and receiver. Here, first the components needed are random integer generator, Dpsk baseband modulator, and additive white Gaussian noise AWGN channel. To observe the waveforms and the scattering plots, we need discrete time, eye diagram, scope before AWGN and after AWGN. To observe the discrete time scattering plot, we need the constellation block before AWGN and after AWGN. Now, let us drag and drop all the components from the digital library. So, this is the library source. So, in the library, browse library, take random integer generator. Let us drag it into the model, and we need eye diagram, we need constellation diagram. So, we need these 2 times. Now, we need AWGN and Dpsk is already been taken. So, let us split this. Now, from the random integer generator, connect to Dpsk and then to the channel. Now, to the eye diagram. Next, here. Next, before and after AWGN. Let us connect it. Now, this is how the connections are made. Now, the connections are over. Set the time to infinity as we did for BPSK and QPSK. In the random integer generator, set the size to 1 or 2. In the Dpsk model, set the MRA size to 2, and in the AWGN model, set EB by N0 to 30. So, repeat the same experiment for different sizes of signal to noise ratio. Now run the simulation. If we run the simulation, we get different eye diagrams. This is before AWGN and this is after AWGM with a signal to noise ratio 30, and this is the constellation diagram of Dpsk after AWGN, and this is the constellation diagram before AWGN. So this is the scattering plot we can observe. Now let us change AWGN to 10. Here now we can observe different waveforms as signal to noise ratio is changed. So this is before additive white Gaussian noise, and this is the signal. This is the output waveform. We are getting signal to noise ratio for 10 after AWGN, and this is the constellation diagram after AWGN, which is a scattering plot, and this is Dpsk before AWGN. Now let us stop the simulation. Here the outcome of the experiment is, after the completion of this experiment, we will be able to know the scatter plot and the eye diagram of Dpsk for different signal to noise ratio. Thank you. Thank you for watching the video.